Well, let me start by thanking the organizers. It's my first time in Brazil. It's a great workshop. So this might sound very obscure. It's a report on a program that we have been following for some years, spearheaded mostly by Max Rota. So it's based on a whole number of papers, but primarily on this latest one from last winter. So, as I said, this might be a rather unfamiliar set of words, and there will be lots of constructs that I'll talk about. So let me sort of start by contextualizing what is it that I'm talking about. And to contextualize things, we want to ask how do we abstract sort of from the full physics, the interesting parts. So if we, of course, the full information about the system can be described by some density matrix. And in the holographic context, we're used to this, by now, this marvelous idea that lots of this physics actually geometrizes. And the bulk metric manages to capture even strongly genuinely quantum effects on the CFD side. And, well, you might, this is a lot of information, and so one might consider distilling it down by, for example, focusing on a particular subsystem, let's say A, tracing out everything else, and asking about the level of mixedness of that subsystem. So that's captured by these entanglement entropies. And in fact, in the geometric context, we have a very nice prescription of how do you extract these entanglement entropies from the bulk geometry if this subsystem is specified by some spatial region in the on the boundary of ADS in the CFT. So that's all well and good, but we don't really want to consider sort of infinitely many possible regions or subsystems. So we might say, well, let's pick some finite set of them. Let me call that number n, some n regions, A sub I, and then ask only about the entanglement entropies of this collection of regions and the composite ones. Okay, so I can collect such entanglement entropies into what I'll call the entropy vector. So now we have distilled the information to just some finite set of real numbers. And in the bulk side, we can sort of do a similar type of thing. We can get rid of the detailed information about the full geometry. And once we have specified these subsystems, we can construct a so-called holographic graph model, which is also a discrete set of data, discrete set of real numbers, which you can think of in some sense as desiccating the space-time in a way where the graph weights allow you to extract the entropy vector very efficiently by a so-called min-cut procedure on the graph. Okay, so now we have a finite set of real numbers, but it doesn't end there. We can go still further, and we're often used to in physics to the fact that maybe the precise numerical values don't matter so much. What really matters is the relations between them, and here. Well, I said before that we have entanglement vector that's bunch of real numbers. Of course, in the holographic context, those entanglement entropies would have been infinite, but for us, you can equivalently work with finite quantities, in particular the mutual informations between pairs of disjoint subsystems. Okay, so one can equivalently use that, and so all the infinities that are really in the entropies we don't need to care about. So I'll push that under the rug in the standard way and think of the mutual informations. But now, instead of asking how much are two systems correlated with each other, in particular, what is the value of the mutual information, I will only ask are they correlated at all or not? It's a binary question. Yes or no? Are these two particular subsystems correlated or are they uncorrelated? So that sounds like a drastic reduction of the information. It's what we will call the pattern of marginal independence. Marginal independence just refers to the fact that two things are decorrelated. And this pattern means that for all possible pairs of disjoint subsystems, I tell you, are they correlated or decorrelated? Okay, so this pattern of marginal independence is a further distillation of the information that would have been contained in the entropy vector. And instead of having some number, finite number of real numbers, I have some slightly larger number, or actually exponentially larger number of just binaries, just bits, yes or no. But in fact, it doesn't stop even there. So the new well, so far this has been sort of older work. And well, if you do the same thing on the graph model side, you can forget all about the weights on the graph and just, that's what gives you the so-called topological graph model that actually loses more information than going here. But again, it distills it to some discrete data. But you can go further. And in fact, you can, instead of considering all possible pairs of disjoint subsystems, you can just group them. You can coarse grain over the set and group them by the composite system to give a construct which we call beta set. Beta for bipartition. So these beta sets I can just classify in a very coarse-grained fashion into whether all the mutual informations in that set are vanishing or strictly positive or some mixture of those. And I can, in fact, focus on just the positive ones, and that's what will give me this so-called correlation hypergraph. Okay, so these are the two phrases that appeared in the title of my talk. So these are the ones that we'll focus on, and we'll focus, I guess this is not very visible, but we'll focus in this talk on the regime where I have actually fixed finite number of regions, some n number of regions, and I'm working squarely in this regime. Okay, now of course, all this is nice. I have distilled all this information down to just some very small, very compact packaging, but it wouldn't be so interesting if I couldn't then, go back and learn something from this very distilled packaging about the original system. Okay, so we really want to ask, to what extent or under what context can we now actually go back? And well, up here, of course, we know that the classical bulk metric applies in just some corner of the parameter space, large and large lambda, but it has been a quarter century of fascinating work to sort of study the various excursions to probe more of this, but that's well outside of the remit of my talk. And even in this classical context, well, we know in principle how we could reconstruct the bulk geometry from knowing a family of entanglement entropies, at least up to the point in the bulk geometry where you can have a continuous set of HRT surfaces that sort of reach to that place. And sort of maybe more interesting question is, well, how much did this really distill? So you might think, well, okay, there's at least a certain school of thought that sort of says that what quantum mechanics is trying to tell us is that it's all about the correlations between the various subsystems, not what is actually being correlated. And so it might be that, in fact, this does carry most of the interesting, or all of the interesting sort of physics in some sense, but again, that's sort of beyond the remit of my talk. More interestingly in this regime, well, if you have an entropy vector with sufficiently large fine graining and you assume that the physics is tame enough, you might imagine you sort of discretize your boundary space and you assign entanglement entropies to all these small subsystems, and then you can interpolate to arbitrary subsystem. So then this might not be such a bad reduction from approximation to this amount of information. more interestingly, going from this binary specification of whether systems are correlated or decorrelated, how in the world could you figure out how much they're correlated or decorrelated? Well, generically, of course, you can't, and geometrically, this construct would correspond to a linear subspace of the so-called entropy space where this vector lives. So it's generically higher dimensional subspace, but if you have, if you focus on a particular set of quantities of interest for us, the so-called extreme rays of a construct I'll introduce in a moment, then this pattern of marginal independence corresponds to one-dimensional object, and so it actually recovers for you the entropy vector up to some irrelevant rescalings. And in fact, you can go further under some assumption which is very innocuous, sort of almost tautologically sounding, but extremely powerful. You can actually recover this full pattern of marginal independence just from this much more coarse-grained quantity. So that will be sort of the biggest part of the talk after I review all of these other constructs, part of the new stuff that I'll be talking about. And it furthermore turns out that already from just knowing just the set of these positive beta sets, one can directly go to reconstructing this topological graph model and supplement it with knowing the entropy vector, the actual holographic graph model. Okay, so with this part is work in progress, but we can do it in a particular context that I'll tell you about. And a sort of future exploration is, well, you might generalize, this is a very broad type of construction, under what situations, you know, how much further you can enlarge this. So we'll see that by the time we get here, well, in fact, by the time we get here, you can go much beyond the holographic context. And part of the surprise for us is that many things that are sort of feel like coming from the correspondence, the holographic correspondence where you do have some classical bulk geometry, the story extends, or the relations extend far beyond holography, and in fact, far beyond quantum mechanics itself. All right, so that's the plan of the talk is to sort of explain these structures in systematically. So first set will be sort of a review. I'll talk about this entropy cones, the graph model, and this pattern of marginal independence. And then go on to introduce these beta sets and the correlation hypergraph. Okay, so let's start with the entropy cones. I'll be very fast because you have all heard nice introductions of various aspects of this. So we have the usual setup where for a given subsystem, we can take the von Neumann entropy of the reduced density matrix. That's what we're calling these entanglement entropies. And so we imagine in the CFT we have specified some number of boundary regions. Those are our subsystems. We can call everything else the purifier. So we can consider sort of a pure state on the entire thing, and we collect the subsystem entropies into this entropy vector. So we have the entropies of the individual regions, but also the composite ones, like A, B, and so forth. So there's 2 to the number of subsystems minus one because we want something to be there. We don't want entanglement entropy of just the empty set. So there's exponentially many. The dimension of the entropy space is this D, 2 to the n minus 1. And we want to, in principle, focus on, well, arbitrary but fixed n. And we have sort of in mind of trying to distill the physics to the extent that we can talk about arbitrarily large n. Okay, so of course, when you want to do things explicitly, this is exponentially large, and many other things are sort of doubly or even triply exponentially large in n. So it's not an easy thing to try to put on the computer or something. But the relations that we distill out of it, the hope is that that won't matter. The explicit expressions won't matter. So we won't be stymied so much by the sort of very rapid growth. So in this entropy space, you can ask, what are all the possible entropy vectors that are constructible from some system, from some quantum system, or in our case, for some holographic system. So take any holographic CFT, any geometric state in that, in whatever dimensions you want, and however excited a state you want, and all that. And for each of those things, take its entropy vector and ask what's the collection of all the allowed entropy vectors. Okay, so it turns out that this structure has a structure of a convex cone, in fact a polyhedral convex cone, in this entropy space. So the entropy space has as axes the individual entanglement entropies. So for example, if you have only two subsystems, A and B, you have a three-dimensional entropy space with axes entropy of A, entropy of B, and entropy of A union B. And in this d-dimensional entropy space, you can characterize this entropy cone in two useful ways, which are sort of complementary to each other. One, you can specify all the sort of relations that restrict where these entropy vectors could lie. Okay, so that gives you the facets of this entropy cone. The complementary view is to specify a collection of extreme rays, which are one-dimensional objects in this entropy space, one-dimensional rays, and the cone is a convex hull of these rays. So if you have a polyhedral cone, there's a finite set of these extreme rays and finite set of facets. Okay, so this for two parties, this really is the cone, and in fact, it is both the holographic entropy cone and what we'll call the quantum entropy cone, which is the set of all the possible entropy vectors admitted in any quantum system. And so, in fact, it's useful to consider an even larger hierarchy of these entropy codes in the entropy space. So the holographic one is the set of all the holographically realizable entropy vectors. The quantum one is all the physically realizable entropy vectors for any quantum system. But the hero of the story will be a much larger cone, the so-called subadditivity cone, which is the set of all the entropy vectors that's delimited by all possible instances of subadditivity, which is just a statement that the amount of correlation between any two subsystems cannot be negative. Okay, so it has to either vanish or be strictly positive. And so each of these subadditivities will form a hyperplane that restricts the allowed space, and so this will be the construct we'll be dealing with most. So here's a cartoon of like a two-dimensional cross-section of the entropy space that doesn't go through the origin. And you can see, of course, from the definition, it's obvious that there's this nesting, because any quantum state has to satisfy subadditivity, and holographic states are a subset of these quantum states. And in fact, you could specify a more refined hierarchy of various cones in between. For example, you could have specified all the entropy vectors compatible not just with subadditivity, but also strong subadditivity that would still contain the quantum entropy cone and, of course, be contained in the subadditivity cone. But we choose not to take that construct for reasons that will hopefully become clear in a moment. For two parties, all three of these cones coincide. That's the picture I showed on the previous slide. But for larger, any more fine refinement of your boundary, they're strictly nested, and in fact, there's a huge gap between them. They get exponentially, separated in this nesting. Yeah.
The restrictions are linear. You are thinking on the cone. It could be non-linear or something like
The quantum entropy cone we don't really know much about. You might rather think that maybe there's sort of infinitely many linear inequalities. It's hard to make sense of the nonlinear ones, partly because of this divergence, and how can you regulate it sensibly when it's not linear. So we'll just be thinking about the linear ones. But I don't know a rigorous statement that there aren't the nonlinear ones. Certainly for these two, we can construct the extreme rays, and we know that the inequalities are obeyed. So those, the holographic one and the subadditive one are definitely polyhedral and linear. But for the quantum one, not much is known. In fact, after n equal to 3, for n equal to 4 and more, nothing is really known beyond the fact that it's inside the subadditivity plus strong subadditivity cone. We don't even know whether there's a finite number of inequalities or not. And in fact, one of the somewhat long-standing questions in some branch of QI is exactly what is this quantum entropy cone? How does one characterize it?
The cone doesn't coincide with the bigger one.
It certainly does not coincide with this large one, because it has to.
Okay.
Because this one is just subadditivities,
okay.
Not strong subadditivities. So strong subadditivities would really restrict this quite a lot. Mm-hmm. And it's not really known whether, it might be that the closure of the quantum entropy cone is really just the subadditivity plus strong subadditivity. Without the closure, they don't coincide because there's a bunch of constraint inequalities. Like if you saturate some number of strong subadditivities, then something else has to be positive. Okay, so that's a much richer structure. So a couple of these, well, in fact, large set of these constraint inequalities are known, but no sort of inequalities in the full entropy space without the constraint beyond SA and SSA. Okay. Any other questions? All right, so the last point I wanted to make on this slide is a surprise from a few years ago in this work with Sergio Hernandez, Cuenca, and Max Rota, was that even though this construct, this subadditivity code, which is very primal, again, it's just a statement that two systems can't have negative correlation, sort of a intuitively obvious statement. Nevertheless, if you knew all the extreme rays of the subadditivity cone that are compatible with geometric states, which are sort of holographically realizable, then, well, and you knew that for more refined system, so some larger number of parties than the one you're interested in, then you could project from here these extreme rays, these holographically realizable extreme rays of the subadditivity cone to obtain all the extreme rays of the holographic entropy cone at the smaller number of parties. And so this innocuous statement of correlations can't be negative actually seems to be very powerful in constructing for us, in principle, this holographic entropy cone. And one might fantasize that that sort of thing extends beyond holography to say if you have some system, like just quantum, any quantum state, if you knew all the extreme rays of quantumly realizable, all the quantumly realizable extreme rays of a subadditivity cone, that projecting them down and taking the convex hull would construct the quantum entropy cone for you. Okay, that's a fantasy. It's not even a conjecture, but there's data for that working for the set of stabilizer states. So the stabilizer cone at some n equal to, up to n equal to 5 or something, we can reconstruct that way. So it's possible that, this just knowing for arbitrarily refined state, what are the admissible patterns of correlations and decorrelations in a given system allows us to extract the cone and therefore indirectly all the inequalities that bound the system.
I think I'm missing something. I'm not parsing this right, so I don't understand. I think you said that you can, by this process of considering the subadditivity cone with more parties, you can deduce the holographic entropy cone for less parties. But what confuses me is, surely you could apply the same argument to the quantum entropy cone. But the quantum entropy cone and the holographic entropy cone are known not to coincide. So if I apply the same construction to do each one, how do I get different answers?
You do it on the set of either quantumly realizable extreme rays or the subset of the holographically realizable ones. Those two sets are not different. They're like GHZ state is a quantumly realizable extreme rays of the subadditivity cone, but it's not a holographically realizable state, the extreme ray of the subadditivity cone.
So I'm confused about where you're, at which, well, maybe you're going to say more about this, but I'm confused about at which level you are identifying these extreme rays and making use of the knowledge of what they are.
So we go to some larger n.
Yes.
We look at all of these extreme rays. Some of them are holographically realizable at that larger n. Some of them are not, but like GHZ are still quantumly realizable. Now we coarse grain. We say, okay, well, I can't distinguish party A from party B.
I see.
And I reduce it down to n in all possible ways.
How do you determine which rays are holographically realizable at?
So that's probably where the crux, where the physics actually does come in.
Yes.
And that's part of what I'll be talking about.
Great.
Okay, and I want, in fact, I'll be talking about both the question of the quantumly realizable and the holographically realizable, but indeed, so. But certainly the sets are distinct, and therefore the cones that you get at the end of the day are distinct. Okay, any other questions before I go on? Okay, so the statement that I just made is subject to a conjecture. It's subject to a conjecture that for the aficionados, as a preview, all the holographically realizable extreme rays are realized by holographic graph models that are so-called simple tree graphs. Tree graphs. I'll explain what that means later on, but that's a caveat. So far, we don't have any, we have strong evidence for the conjecture, but we don't have any proof. So that statement rests on this conjecture. Okay, and of course, I haven't really told you what is n prime in terms of n. We have an upper bound on n prime in terms of n, but that's a very weak upper bound, and it's at a ridiculously large upper bound. It's again some exponential thing. But in practice, when we do this for, say, n equal to 5, we only need to get to n prime equal to 8 or something, so maybe it's not so, we haven't really bounded it sharply. So that's more of a computational problem than a conceptual one. All right, so that's the entropy cones. Now, the subadditivity cone, which I said was the hero of our story, is delimited by this subadditivities, which is a statement of the non-negativity of mutual information, which is, of course, this combination of entanglement entropies. It satisfies this positivity, that's the statement of subadditivity, well, positivity meaning non-negativity. And it satisfies monotonicity under inclusion, that's the statement of strong subadditivity. If two systems have some amount of correlation, if you enlarge one of them, then the amount of correlation can't decrease. It can only increase. Okay, both of those statements are very intuitive. Okay, and we will not take this one into account at all. Directly, we'll take a weaker sort of approximation of it, which I'll describe in a second, but what we will focus on is just this cone built out of these subadditivities, the statements of this non-negativity of correlations. So now, if this can be saturated, of course, and if it is saturated, then that's tantamount to the statement that the combined density matrix, combined reduced density matrix for the reduced density matrix for the combined system factorizes in this way. So that's referred to as this marginal independence. All right. So holographically, what does that mean? It's tantamount to basically a very nice geometrical statement. So if you have a, let's say just as a cartoon, if you have a two-dimensional space, you specify some subsystem A, here would be, okay, and this is all described in the static context, so this would be just the minimal surface that's homologous to A, and the slice at this constant time of the entanglement wedge, or the more strictly the homology region between this, is going to be disconnected between two, for a composite system AB, if the mutual information vanishes, assuming, as we specified in this paper more carefully, assuming some genericity, not being on sort of phase transitions and so forth, but generically it's disconnected if the mutual information vanishes, and it's connected if the mutual information is positive. So geometrically, this pattern of marginal independence really tells you about connectivity of entanglement wedges in the bulk for that given state in that theory and so forth. Okay, so it is a very nice geometrical interpretation. So you might well imagine that if you knew which entanglement wedges can be simultaneously connected or disconnected, you would know a lot about the bulk geometry. Okay, so now the specification of which pairs of disjoint subsystems can be simultaneously correlated versus uncorrelated is, well, again, this is what I just said, holographically corresponds to the simultaneous connectivity of the entanglement wedges. This geometrically or mathematically constitutes a linear subspace of entropy space, because the set that you specify which is vanishing, complement of which is the one that is strictly positive, the set that is vanishing corresponds to hyperplanes. Each one of these equalities is a hyperplane in the entropy space, and so if you have multiple ones of them imposed, it's the intersection of these hyperplanes, and therefore it's a linear subspace of the entropy space. Okay, so in this cartoon for n equal to 2, for example, if you saturate, so this would be like subadditivity between A and B being saturated. This one would be between A and the purifier, and so forth. So if you saturate both of them, you're already on this extreme ray. Okay, so in any case, this now has this pattern of marginal independence as a discrete structure, some specific set of hyperplanes, okay, which are constitute this hyperplane arrangement in the entropy space. And the more decorrelated pairs you have in this pattern, the simpler the system. So one can nicely see this on the holographic graph model. So let me just briefly introduce that. So that's the thing that sort of distills in the bulk just discrete set of data that suffices to construct for us the entropy vector, which was already formulated in this paper from a decade ago that initially formulated the holographic entropy cone. So the prescription is as follows. So you start with so here's the spatial slice of a boundary. You specify your subsystems, and of course your state. And from that you can figure out where all the RT surfaces are. And those partition the bulk into cells, the various sort of intersections and complements of the entanglement wedges. And each cell gets a vertex assigned to it. That will be the set of vertices for our graph model. Each set of a pair of adjoining cells gets an edge between them. So the edges in the graph corresponds to adjoining cells. They adjoin across a part of an RT surface. And so you can naturally assign them weights based on the area of that RT surface. And then you can determine the entanglement entropy by just taking a min cut of this graph. So you look at, for example, for subsystem AB, you ask which cut in these edges that's homologous to AB would have the smallest cost, and that's the That's the entropy. Okay, so I won't need too many details of this, so I'm not going to go any more in depth. This is just to indicate what sort of things come in to get an entropy vector out of something discrete. Okay, so if you have intersecting RT surfaces, you always get a loop like this. And if you don't have any loops like this, that sort of a graph is called a tree graph. And if every boundary, so boundary vertices are the ones that resulted from the cells that adjoin to the boundary. If each boundary vertex, if there's only one boundary vertex per party, like I don't have A here and A here, then such a graph is called simple. And the holographic graph model, well, and I call the holographic graph model the thing that has these boundary vertices all labeled and that has the edge weights. And I call a topological graph model the object without the edge weights. Okay, so that's just some nomenclature. And now let's go back to the statement about correlation versus decorrelation. So let me illustrate it with an example. So suppose we take a 2 plus 1 dimensional CFT, 2-dimensional boundary space, and we specify 4 regions that are all, close enough to each other such that they are all pairwise correlated, and therefore they're correlated multiply. So for example, the RT surface for AC would be like an arch between AC, but between B and AC would be like this three branch arch and so forth. And all these different arches overlap in various ways. So you can imagine already it forms a large number of cells. In fact, it forms, it forms 81 of these cells with 185 connections between them. So it's a mess. Okay, that would be the holographic graph model for this innocuously simple configuration when you assume, let's say, vacuum state. But now let's do the exercise of saying, well, let's move this one a little bit further away so that it stops being correlated, let's say, with B, but it's still correlated with everything else. And so here I started out with empty set of vanishing mutual informations, small empty PMI, and now I added the mutual information between A and B vanishing to it. Okay, so I added the pair AB, and now the graph is slightly simpler. Now if in addition I decorrelate C from A, so I add a C pair, it simplifies, and I keep going until the thing decorrelates so nicely that now we just get a tree graph. In fact, we get a simple tree graph already at this stage.
Hey, Veronika, sorry, can I ask a question about to appreciate the simplification here? Can you go back to the previous slide and say, what is the, like combinatorially, what is the question to which the answer is 181? No, 81 or 185. What are we,
so
what exactly is being?
What is it? So let's say we have an arch. Well, we have a dome over A, dome over C. Those are two regions that are two of the vertices. That would be this vertex and this vertex. We also have an arch over AC, and we can ask what set of points are inside the arch but outside of the two domes. Okay, so we can keep doing that with all these different arches. So you can ask what is outside of, let's say, ABC entanglement wedge, but still inside ACD entanglement wedge or something, and outside. So for each possible entanglement wedge, you specify a bit string of whether it's inside or outside. Okay, that would be exponentially large, but not all things are allowed because, as you know very well, it's restricted by nesting. And so, by entanglement wedge nesting. And so you can have only limited sets of combinations of these bit strings, and in fact, it's not even, that goes doubly exponentially, and in fact, it's not been calculated what is this after n equal to 9 or something. But anyway, for this n equal to 4, it's simple enough, and this is just telling you how many possible bit strings you have.
So just so let me try to see if I understood. So we have 4 named regions, A, B, C, D. So then we have 15 different combinations of like amalgamations of them that we can make.
Dimensional. You have
so then
15 different subsystems.
Then you can be inside or outside any of these entanglement wedges.
Exactly.
So it's 2 to the 15, but that's an overcount because of nesting. And after you account for nesting, 2 to the 15 goes down to 8 to 1.
Yep, exactly.
Thank you.
Anything else? Okay. Okay, so that's the. So it's clear that if you put in, so there's some Stirling's number worth of these pairs. Okay, that scales like 3 to the n at large n. There's only something that scales like 2 to the n worth of dimensions in the entropy space. And so clearly there's many linear dependencies between these equations. But suppose you have, in d-dimensional entropy space, if you have d minus 1 linearly independent collection that you have imposed, well, then the intersection has to be already on one-dimensional structure, one-dimensional pattern of marginal independence, and that often reduces already to something that is a tree graph. Not necessarily a simple tree graph, and here is a conjecture that it works for anything, any extreme ray, but let me not get into the weeds. But it's clear that you get a one-dimensional PMI once you have sufficiently many of these things decorrelated. And this is in fact how we could construct the set of holographically realizable set of extreme rays of the subadditivity cone, to answer Don's earlier question. That's not how we have done it, but you can imagine doing it this way.
Maybe I have a quick question. So I think in the one of the previous slides, you showed how to construct the graph. It was sort of implying that it is a holographic picture because it started from some circle and
good.
But then you got a graph with a loop.
So yes, the construction that I have done so far was starting from the holographic graph model. We'll see that the structures that we get generalize much beyond that. So this will have been a crutch that we throw aside and transcend this context. But at the end of the day, we do want to, if we want to ask what are all the extreme rays of this subadditivity cone that are realizable holographically, it's already in this paper from 10 years ago that defined the holographic entropy cone. It was argued that the entropy cone corresponding to all graph models, any graph with any set of non-negative edge weights, giving you entropy vector by this min-cut prescription, that cone and the holographic entropy cone actually coincide. So for any bulk geometry, you can construct a graph, but conversely, from any graph, you can construct some bulk geometry. Okay, the construction is not unique. You can construct many different geometries, but because of this correspondence, one sort of expects. This is just to, the argument was more careful, but the intuitive justification is you can go back and forth, and so the cones coincide, and you can therefore analyze the holographic entropy cone by considering the simpler sort of set of building blocks of these holographic graph models, which are at least discrete structures. Yeah.
Can I just clarify one thing? So here, from that setup that you're saying, should I understand that A has no correlation with its complement?
A has correlation with its complement. That's a statement that the graph is actually connected to the rest of it, but it has no correlation with whatever was B at this point.
But then, well,
but just B. But if you enlarge B, it already has correlation with BC. Okay, we haven't yet thrown out in this step. It has correlation with BC and BD and so forth.
I had understood that it has no correlation with B or C or D or O.
So here at this stage, A has no correlation with B and it has no correlation with C, but it still would have correlation with BC and so forth. So this is just a specific. You can go down in many different ways. You can, at this stage, you could have really correlated BC without decorrelating D and so forth. The only thing that you have to be implementing is this sort of weaker version of SSA, where that if two things are decorrelated, then their subsystems must be also already decorrelated. All right, I'm running very far behind. This was all supposed to be part of a beginning of a review. So I haven't gotten to the actual topic of the talk. Okay, this pattern of marginal independence. Let me sort of motivate why we are interested in this. So quantumly, we know that the sort of quintessential part of quantum mechanics is that even if you know everything about the whole system, you don't necessarily know anything about the individual subsystems of that. Okay, that's the statement of entanglement. But you might now want to ask the converse question. You know, suppose I give you full information about subsystems, can you tell me whether there exists a combined system that would have such subsystems? Okay, this is formulated as the quantum marginal problem, not marginal independence, but quantum marginal problem. So given some collection, not necessarily all of them, but some collection of these marginals, does there exist a density matrix implementing all of them? This is a very hard problem, unsolved. In fact, it's in the complexity category. That's some generalization of NP hard, or Arthur Berman class or something. And there's very simplified versions of it that are easier, but that's beyond the scope of this talk. But you might sort of retreat to just asking, never mind about does there exist a full density matrix, but does that, well, sorry, never mind about giving you this reduced density matrices, but suppose I just give you the entropy vector itself. Suppose I give you even the full thing. Okay, so D numbers, for these D numbers, does there exist a density matrix that incorporates all of them? Even that is too hard for us at present, although we are getting towards a prescription for ascertaining whether or not there is a holographically realizable such, well, constructing something that, you know, eventually might get to this stage. But for now, we have retreated all the way to this marginal independence problem, which asks, given just this pattern of marginal independence, the set of vanishing mutual informations, does there then exist a density matrix implementing that pattern? Okay, and if we restrict to a specific system, say quantum mechanics, then this would be called the quantum marginal independence problem. In holography, we called it the holographic marginal independence problem. So each theory would have its own sort of marginal independence problem. Okay, so not all pairs of, well, not all pattern of just, if I tell you, you know, this set of pairs are decorrelated, not all such things are realizable for very obvious reasons. They can have inconsistency, which I call mathematical inconsistency or physical inconsistency. So here it's just it could be violating an identity between such mutual information. So say 3 of these I declare are 0, and therefore the last one would not be, I declare implicitly is not 0, but that would violate an identity that these two sides should be equal. Okay, there are many such identities because, as I said, the number of these mutual informations is exponentially larger than the dimension of the entropy space. The physical inconsistency, by that I mean things like violating the subadditivity or strong subadditivity. So for example, if I tell you these two are 0, well, by subadditivity, I know that these can't be negative, and therefore a sum of non-negative things being 0 means that each one individually is 0. So these two must be inside the PMI if these two are. Strong subadditivity tells us this. In particular, I mean a weaker condition that if this is 0, then anything smaller must be 0. And in fact, this is what we dubbed the Klein condition. Okay, that's the KC that appeared on the first slide. And this is a very, I mean, again, it's an innocuous sounding statement, but it turns out to be immensely powerful. And this is the thing that we're using instead of imposing SSA. We're just imposing this Klein condition, and we're getting an incredible amount of mileage out of it. Okay, so because of this, we're tempted to organize these pairs of disjoint subsystems into a poset structure, partially ordered set, where the ordering is based on sort of the inclusion. So, A, B would be below A with B, C. So you can sort of visualize this on the Hasse diagram, where the list of all the mutual information pairs, like A with B, C, and so forth, you can order where this ordering would be, A, B is below A with B, C, and so forth. You can have, of course, B with AC is below, A with C is below B with AC because there's a symmetry between the order of these arguments. And there's, in the second row, there's sort of two types. You can have 3 things below it or 4 things below it. It gets more complicated as you go up if you have larger n. So this would be the set of all such relations. And once you have this Hasse diagram, this poset structure, you can formulate constructs like a downset where you start with some element, you identify the ones below it, and you go all the way down. And this would be a downset. Similarly, you can start somewhere and construct its upset. And in fact, the upsets and the downsets are complementary to each other in this nice way. So that's one type of construct. Another type of construct is a so-called anti-chain. So things that don't have any relation between them. So for example, any subset on this row doesn't have any order relation between anything else. So this would be an example of anti-chain. But even this would be an example of anti-chain because if you take the futures and the pasts of all these things, they don't, futures and the things that are greater in the structure and smaller in the structure are mutually disjoint. I find it personally very helpful to mentally have the sort of think of this as future sets and past sets in sort of causal structure of space-time because it makes things very intuitive for me. But okay, so this linear dependence of a pattern is implemented geometrically by saying that defining PMI or restricting to what we mean by PMI is simply something that's a face of this, span of the face of this subadditivity cone, and that automatically takes care of all these linear dependencies. Okay, so we have now reduced the set of all possible specifications to just these faces of SA cone, so that's a drastic reduction, but the one that's allowed by this Klein condition is to take a downset in the MI poset, and that's the structure that allows us to, well, that automatically implements this Klein condition. Okay, so that's, and the reduction is quite impressive. So for n equal to 3 already, if I tell you a PMI of a certain dimensionality, let's say one-dimensional PMIs, which are the extreme rays, the total number of extreme rays of n equal to 3 subadditivity cone is 11, but the ones that are compatible with KC is just 7. So these are the 6 Bell pairs and the 4-party perfect tensor. Similarly, for 6-dimensional PMIs, which are the facets, instead of 18, you have just 6, which are the statements of vanishing mutual information between just A and B, or all these singletons, but not with A and BC, because that would not be a facet, because you would need, also to include the A and B and A and B, A and C, and that would be already a lower dimensional thing. All right, so that's for n equal to, for n equal to 4, this was more impressive. Okay, but the reduction is more drastic, and it's of course more and more drastic with higher n. So that's just to illustrate the power of this, applying this condition on singling out which patterns are even have a chance of being admissible. Of course, many of these are still not admissible, but anything in the complement is definitely not admissible. All right. So, okay. 5 minutes, and that's the beginning of the talk. Okay. Okay, so the beta sets, okay, let me just flash. The beta sets are coarse graining over this mutual information poset, where you coarse grain by grouping everything that has the same composite argument. And the fraction of the number of all the possible beta sets versus all the possible mutual information gets exponentially small with large n, so it's a drastic reduction. You can specify order relations between these coarse-grained objects by just simple inclusion. And in fact, in some sense, they coarse grain the Hasse diagram relations. I don't know if you can even see them for the mutual informations. All right, and now the question is, how do we go back? How can we specify these beta sets as such to specify the pattern of marginal independence? Okay, you can sort of ask which are the set of vanishing mutual informations and which are the positive ones, and now define a beta set to be vanishing if all the mutual informations are 0, or positive if all of them are positive, and partial if they're mixed. And you can furthermore characterize the beta sets in an independent partition of whether some of these mutual informations lie in an antichain that generates the positive mutual information upset in the MI poset, or whether some mutual information are, this is what we call essential. If all of them are in this antichain, we call it completely essential. And if none of them are, it's not essential. Okay, so we have this sort of partition of the classification of the beta sets, and holograph, well, okay, let me actually skip this because that would take a bit of time. And here are some examples which I'll also skip, but the point of the construction is to show that if you start with some, let's say, generating element for the vanishing mutual information, you take its down set, you take identify complementary upset, which is generated by this antichain, and now when you're grouping these mutual informations into beta sets, you can already figure out from this classification which is which. So the color coding gives you the classification, and in fact such a classification is realizable, and you can realize it by this graph model, which basically tells you that you have these 4 bell pairs, and there are 2 things that are decorrelated. And you can do that for various other types of examples. Here would be another downset which is realizable, but now, for example, this would be not a positive beta set, but a partial one, and so forth. Okay, there's ones that look similar, but that are not realizable, because in fact it turns out that there are things that would violate these linear relations. And so from this set of information, we can sort of try to distill the PMI. The key theorem here, was that, let me just go back, is that all essential beta sets are actually positive. Okay, and that has a lot of power. It reduces this partition into a smaller set, which one can then go and classify. Okay, too much out of time, so I'm going to jump to the sort of end. The main key point from this part was that, okay, let me try to take 2 minutes and see if I manage. The key point of this part was that we can actually recover the entire PMI from just this beta set classification. Okay, now geometrically, this to demystify the essentialness is if you know that, for example, two beta sets are positive, so 2 entanglement wedges are connected like this, then by entanglement wedge nesting, the communal one is also connected, so it's also positive. And this statement, however, we can prove for these beta sets well beyond the holographic context, in fact, well beyond the quantum context, where we don't have a pattern that's realizable even quantumly, but nevertheless, this type of statement still holds. Okay, I think that's something deep, which we have yet to make full use of, but I think this is at least a pointer to the sort of utility of this framework, of this formalism that we have invented. Okay, and this structure really encodes, what it does for you is encoding the factorization of the marginals of the full density matrix. Now, this correlation hypergraph was a graphical way of collecting the positive beta sets. Okay, let me skip over all of this. This is going to be a construction of this hypergraph, and you can ask me about it later. So this would be a hypergraph. This would be a so-called line graph constructed from it. And the structures are some things that are allowing us to construct a graph model. The key thing there is a graph which has no sort of chordless cycles that have chordless squares or higher cycles. And such chordal graphs, well, an entropy vector, the key theorem of our paper is that an entropy vector can be realized by a simple tree graph only if, first of all, its pattern of marginal independence satisfies this Klein condition. But secondly, this line graph that I just flashed on the previous slide of this correlation hypergraph is chordal. And this is a condition that can be tested efficiently. Okay, so we can test efficiently without any of these explicit constructions directly from being handed an entropy vector. We compute its PMI, we compute the corresponding beta set classification, we take the correlation hypergraph, and we check whether its line graph is chordal. That will tell us immediately whether there is a simple tree graph model for it or not. Okay, so that's a very fast way of figuring out what happens, and this can be done efficiently. You can get more complicated graphs which don't satisfy this chordality because they're not simple, but at least you might imagine that that's okay because you can sort of fine-grain this to get a simple tree graph for higher n, and therefore all you ever need to know is simple tree graphs, and this is how you would identify these holographic extreme rays without doing any further work. So this is the hope, that you can then reconstruct the holographic entropy cone. Okay, and so it allows us in principle to specify the full holographic entropy cone. This was a cartoon of what I said earlier, and we have a conjecture that this chordality is not only necessary, but it's also sufficient. And the summary was, okay, to explain these relations, and the key points are that this beta set characterization seems to be very efficient, and the upshot of it is that we might be able to extract this full holographic entropy cone without ever having to go through finding the inequalities and so forth. Okay, so let me stop here, and thank you for your...
Thank you very much. Are there questions for Veronika?
Can you explain again how, given the tree graph, you can obtain the extreme rays?
Okay. Good. It's not again, I haven't yet explained it. But you mean the earlier thing on the holographic graph model, or you mean the hypergraph?
No, the hypergraph. You have this tree-level graph, and then you said that you can obtain all the amount of extreme rays.
Good. So let me just sketch the sort of a construction that you might have. Let's see. Okay. So here is an example how we could go. Continue to mirror. Okay. Here's an example. Secretly, I'm going to reconstruct this holographic graph model where all the edge weights are 1. From just the entropy, well, I can read of the entropy vector, and suppose I'm handing you the entropy vector without actually telling you whether it's realizable or not. Okay, so from the entropy vector, I can figure out all the mutual informations, figure out whether they're 0 or not 0, collect the 0 ones to PMI, classify the beta set. So here is the black ones are the 0 ones, the white ones are the non-zero ones. And when I do this classification of constructing this anti-chain and so forth, I end up with, oops, now I went too far. I end up with this classification of the beta sets. Now from these beta sets, I take the set of positive ones, which are these warm-colored ones, and I construct from them this correlation hypergraph is just a specification of hyperedges, which would be this ABCD, ABC, and so forth, for each possible subsystem. The vertices of a hypergraph are the individual singletons, A, B, C, D. The hypergraph edges are corresponding to the subsystems that have positive beta sets. I take its line graph, which is an intersection graph of this hypergraph, where each hyperedge becomes a vertex of the line graph, and each edge, and there's an edge between two vertices if the original subsystems are overlapping. Okay, so that's a line graph. This line graph for this one, Okay, the line graph of this correlation hypergraph looks like this. So I had these positive beta sets, and now I'm drawing an edge between them whenever two things overlap. So notice here that there is no edge between A, B, and CD because those things don't overlap. Okay, now I construct a max-click graph. Max-click, well, I can explain later what these things are, but the max-click graph for these correlation hypergraphs, and there's a procedure now to construct clicks for every single party. And in this click graph, max click graph, I have just 2 max clicks. That gives me a simple edge like this. And each party ends up sort of a leaf growing out of a unique vertex in this simple tree graph that's going to reconstruct this graph like that. Okay, so the real power in between is the statement about that relates to a so-called tree hypergraph that you can construct using this max clicks. Okay, so I can sort of explain that in more detail. This is in a work that is yet to appear, hopefully not so long from now, but there's a very specific procedure to sort of implement this, at least for these simple tree graphs.
And just one last question. This click graph condition is related to your Klein conditions for the model information?
Well, no, no, but the whole construct of this correlation hypergraph rests on having imposed this Klein condition.
Okay. Okay. Thank you.
Can you briefly say again exactly where you input holography in all of this? Because
good.
It seemed to have gone very much to the background.
Excellent. Yeah, so there are two places. One place is the fact that we're using, well, it's basically the minimality in the RT formula, which allows for phase transition. So I'm describing the entanglement entropy. So basically, if you consider the surface corresponding to a composite system, either it's a new surface, like entanglement wedge for the AB can be either a new thing, a connected entanglement wedge, or it's composed from the one for A and the one for B. So I'm recycling surfaces if and only if, generically, the mutual information between those subsystems vanishes. Now, of course, outside of the classical remit, the mutual information never vanishes. It's bounded below by at order 0, not order n squared by the correlator, but at the classical limit, we don't care about the order 1, order n to the 0.
Is that the only input, really, or?
Well, okay, so that's the one thing.
Yeah.
The other thing is in this cartoon of nesting of these entropy cones, I said that we can recover the holographic one from the subadditivity one, knowing which of these extreme rays are holographically realizable. Okay, so that's this marginal independence problem. So basically we have distilled this continuum of information into a discretum, into a combinatorial problem, as it were, of identifying whether or not a given pattern of marginal independence, and just one-dimensional pattern of marginal independence, is holographically realizable or not. And the development with these beta sets and correlation hypergraphs is saying that we can test that efficiently by asking about the chordality of this line graph of this correlation hypergraph.
But that's a conjecture still. That is a complete equivalence with holography.
That's a, yes. It is a conjecture. We think it's true because we have reasonably strong evidence, but of course it is a conjecture. We haven't proved it.
Gotcha.
In view of time, I think that we should thank Veronika for a very interesting talk.
Thank you.
There is a coffee break now.